Hello everyone. Today and next week we'll be learning about radiation detection and measurement. Before we start, let's do some recap. Last week we learned about exposure and karma and dose and how we can measure dose in the medium by using these features. So exposure, what is exposure? Exposure is by definition a measure of the ability of photon beam is only defined for the photon beam that is lower than 3 mega electron volt to ionize air. So again, exposure is specifically designed or rather defined for the air. So conceptually, it is total charge over mass of air. So it is Coulomb per kilogram in SI unit, and traditional unit is in Röntgen. So 1 Röntgen is 2.58 to the 10 to the negative 4 Coulomb per kilogram. Then we talked about karma versus dose. So karma is by definition is kinetic energy released, just focus on released per mass, per unit mass. So it is the sum of all the initial kinetic energy of all charged particles. So it is liberated by uncharged ionization particle beam. So photon coming in, and then it liberates electron, right? So how much energy is basically transferred to that charged particle, okay, for any given mass. Whereas in observed dose, it is a total energy absorbed, rather than released. It is how much is actually absorbed, right, from indirectly or directly ionization radiation. So karma is typically for photon, right, but also neutron. But observed dose can be defined for any particle. So graphically, karma can be explained like this. So photon, which is uncharged particle, coming into the mass, and then it'll transfer its photon energy to charged particle, which is electron, right? And then electron will travel within the mass, and it'll create ionization, right? Right? So that ionization of the electron can create follow-up photons, or even higher electron can create its own daughter track, right? And this scattered photon can escape. So when we define karma, we are talking about how much of the energy is transferred to the charged particle within that mass. Whereas for dose, it is how much of the energy is absorbed within the mass, right? So it is actually, I circled in red here. So remember, all those definition is done by charged particle, right? The uncharged particle itself cannot deposit any dose. Our photon beam treatment, it is not the photon that actually deposits its energy. It's a secondary electron that deposits energy to our patient and to the tumor tissue. So when we define dose, it is this red area where the electron, rather charged particle, that deposits energy using this Coulomb scattering. So remember, karma versus dose, it is that different. Okay, in a nutshell, so exposure. Okay, what do we measure? We measure the ability of radiation to ionize air. That's the definition of exposure, and it is a Coulomb per mass. And then the unit is traditional unit is Röntgen, and then SI unit is Coulomb per kilogram. Okay, and karma versus observed dose. So karma, the unit is the same in gray, but we're talking about the energy transfer versus energy absorbed. So I'm not going to go over, but last week we defined, or we derived rather, so karma can be rewritten into energy fluence times mass transfer coefficient, right? And then observed dose can be very similar to the collisional karma in certain situation, but again, that is energy fluence times mass energy absorption coefficient. So both karma and observed dose shares the unit, which is gray, how much energy per mass, joule per kilogram. And traditionally we use red, but SI unit is gray. And one gray is 100 rad. One rad is 1 centigrade. So exposure may be measured using small air field detectors, right? So we'll learn more about it today. However, what we want to know is those in the medium, okay? So we derived and we showed ourselves that it is possible to calculate the dose from the measured exposure under certain situation. So under charge particle equilibrium situation, those can be rewritten as collisional karma, which is energy fluence times mass energy absorption coefficient. So think about this. So we're defining those in the medium and those in the air. So using the same derivation above, energy fluence and mass energy absorption coefficient for both for medium and air. And then you take the ratio between those two. So you just basically rewriting this, and then you can derive it. Okay, those in the medium is those in the air times the ratio between mass energy absorption coefficient between medium and air, and then the ratio of energy fluence. So some A constant, you can put it in constant in certain situation. And then so we defined, your textbook defined this as F med. Okay, so all this is F med. So on your left is those in the medium, and on your right is exposure, right? So exposure, that's something you can measure using air-filled ion chamber. Okay, so F medium is a function of medium is medium and then photon energy. All right, so that was a recap, and today in chapter 8 in your textbook, we'll discuss the instrument, different instrument that we can measure exposure and dose, and what physicists use. We call it phantom. It is actually some alternative medium that we can use instead of actual live patient. So we'll learn about half of the detectors, and then next week we will learn the other half. We'll categorize those into different, like 3 different categories. One is gas ionization detectors and solid state detectors. And then we can, next page, we have a liquid detectors. But what are the gas ionization detectors? So we are already familiar with this, ionization chambers and GM counters. Okay, whereas solid state detectors are TLDs, OSLDs, and films can be categorized under solid state detector. So we'll learn about films and diodes and polymer gel. So it's not really clinically readily available, but it's very interesting. It has unique features, and we'll also learn about scintillation detectors today. I mean, not today, today or tomorrow, next week rather. And third category will be categorized the liquid dosimeter. So again, these are not clinical detectors, but I've seen RayFax ask about this. I personally don't have a clinical experience with this, but I'll try my best to explain what are those calorimeters and chemical dosimeters. Okay. We physicists love to use this phantom. So when we say phantom, what are these phantoms? So it's a patient substitute for dosimetry measurement. So what kind of phantoms we use? We have geometrical phantoms, as you see in this picture. So it's a slab or cube or cylinder shape, or water phantom. I have some pictures later. And or anthropomorphic phantom. So it looks like human. It is designed per slab, so you can actually open up and break them up. You can put some film in between the slabs, or some phantoms are designed so that it can have some TLD or OSLD insert. So you can actually place these detectors inside this phantom, and then you can irradiate as if it is a real patient, and you can assess some dose without risking your patients. We're looking for material that is tissue equivalent. So especially in our application in megavoltage photon electron range, what we care most is electron density. So material that has similar electron density to that of water. So why is that? So our application is Compton dominant, right? So megavoltage, photon, electron, Compton dominant. So Compton cares about this electron density. So as long as you have a material that has a relative electron density to water, which is very similar to water, then that material is ideal for high energy X-ray application. So what are the typical material? So it's a polystyrene is actually very typical. So it's a material density, electron density that are rather that has 0.97, and acrylic, plexiglass, lucite. These are typical material that we use. Here you're looking at one of the commercial solution. So we call this category as slab phantom. I'm not sure you guys have seen this, but we have a different bunch of these slabs. So this particular example is GAMX, its company. Now actually it's part of Sun Nuclear. They call it solid water. So they have solid water first generation, and now they have solid water HE. It is more strong, but both features water equivalency. So as small as 20 by 20, 30 by 30, and large as 40 by 40. The thicknesses ranges from 2 millimeter slab to 60 millimeter thickness. So it's very similar to water for the range of energies that our applications are. So and this here you can see that these phantoms have like these plugs. So you just pull out this plug, and then you can put in these chambers, ionization chambers for measurement. So this solid water is rather handy because it is cumbersome to set up actual water phantom every month or every morning, that is, so to check the output. So instead you can actually easily handle this phantom. There's no it's a lot simpler. You can easy to move around, and there's no worry about water damage. So it's very handy, and it's very useful for constancy check, right? Month to month output, you can easily check with this solid water. Whereas annual QA, we still measure our machine output. We still adjust our machine output using the actual water that I'll explain later. But again, this solid water solution is extremely handy. Here you're looking at PDD of 6 MeV and 18 MeV. That is either measured in water phantom or measured in this solid water phantom. Okay, so this is measurement in water, that is solid line. Then you have this cross that is measured in solid water, and then circle is Monte Carlo simulation using that phantom material. So as you see, we have 6 MV and 18 MV. They're almost identical on top of each other. Here's an example for electrons. So electron PDD at different energy, showing that the water phantom matches the solid water phantom. Solid water is not the only commercial phantom. So there's another company, CIRS. It's interesting, ironically, both companies, GAMX and CIRS, they're both actually now under the name of Sun Nuclear plastic water. So I don't know how the future product development will be like. But this one is as thin as 1 millimeter thickness. So as you see in this example here, it displays that detector hole for parallel plate chamber. We also have to talk about the actual water itself. We talked about solid water previously, but water phantom is literally phantom like container with water. So we talked about water is actually best substitute for our patient, and this phantom is special that it has a motorized arms. So when you attach a detector into this one of the detector holder, and you can remotely control the movement of this detector holder, left, right, up, down, or in and out, diagonally. So it is best suited for measure depth dose and orthogonal profile or beam flatness. When we say beam flatness, it's how flat our beams for the flattened beams, 6x, or a beam symmetry, how similar our left, right of a profile. You're looking at 9 MeV beam that we measure using that water phantom. So in green is actual measurement. So 9 MeV and 15 by 15 cone under the machine. So you let the beam on for a long period of time, and then you go out to the control room, and then you move your detector left to right, or right to left. Oh, in this, I'm sorry, I take that back. In this example, you rather actually move your detector from surface to down, right? That's how you measure this PDD. So what you see in red is a TPS calculation. So it's showing excellent agreement. So that's how you verify your treatment calculation beam modeling is accurate, right? So 9 MeV. So we don't usually do this, every month or anything, but this is typical part of machine commissioning. When you purchase new machine, or after some major component replacement or service, you want to measure this percent depth dose and characterize your machine, and then you compare that against your treatment planning system calculation. In this example, this is a profile across at different depth. So I'm not sure exactly what depth I measured this, but it is normalized to the Dmax. So this is 100. So this is Dmax, and it is actually depth of D80, right, R80. So again, it's hard to tell which one is which, but measurement versus calculation, they are right on top of each other. So again, this motorized phantom, you can actually program it, you can cue it. Okay, so you don't have to tell every time. You can actually pre-program your water phantom that you do depth measurement, and then profile measurement, and even at different depth you can measure at profile. You can also measure diagonal, etc. So this is a good example, and it gives you confidence that my calculation, what I see in my treatment planning system matches with what I see, what actually patient is getting. So I already mentioned, that those water phantom motorized arms, they can hold certain detectors. So let's talk about some detectors. So this gas ionization detector is one category of it. So this ionization chamber rely on the ability of radiation to ionize its gas. So it has a gas inside, typically air inside. Okay, so as the radiation pass through that active volume of gas, it produces charged particle, right? So we all now know that what ionization is. So whenever there is a charged particle, liberation, you can actually collect those information. So I have some animation here. Let's move on. So in this animation, I'm not sure you can play this, but anyway, so imagine very simple scenario situation where you have active volume here. So this is filled with air, and then we have electrode that is actually applied different voltage. Okay, positively charged voltage here, negatively charged. And then you apply that with this some sort of like a voltage meter, and then you are trying to measure either ampere or coulomb that is actually happening within the electrode. So let's see. So the radiation comes in, and then it ionizes this air. Then you create this charge pair, and what happened is, so it'll be the charge will be collected by this electrode. So positively charged ions will pulled into this negatively charged electrode, and vice versa, right? Negative ions will be pulled into this positively charged electrode, and then there'll be current. Okay, so it'll be current, and you can run in current mode or Coulomb mode, right? So you can actually turn the beam on, and then collect. You turn the beam off, then you collect all, and you just measure the whole charge. Or so that is for the cases for the machines that you can turn on and off. But think about HDR source like brachy source. It's not something you can turn on and off. It is always on. So what do? You measure in ampere mode. You just how much of Coulomb do I get per hour? So it's sort of like a rate, right? All right, let's keep going. So Remember, so exposure is measured in charged particle equilibrium, right? So what is CPE? CPE, the charge produces in the volume, but eventually escapes, like these events, will be compensated by the charges produced outside. Okay, this event here, these two events has happened outside of this volume, right? But the resultant dose deposition is happening in my active volume, so it'll be compensated, and then we can call it is charged particle equilibrium. So just remember that, and we'll come back to this. Okay. To borrow your textbook's explanation, to maintain charge particle equilibrium, you have to have enough shell volume around the cavity that you're interested in, the active volume, right? So the volume, however, the shell volume has to be larger than maximum range of the scattered electron to, maintain CPE. So how can we achieve that? Because it'll be very big. So this can be achieved by replacing this air shell with a solid material. Okay, but that solid material has to have effective Z value that of air. Okay, so if you use some plastic or solid material, you only need very, very thin thickness that is equivalent to the air. Okay, so that's actually a typical example. So it is thick enough, okay, to preserve this CPE condition, but you don't want that to be too thick, because when you introduce very, very thick volume of wall, they can perturb the energy fluence within that field, right? So we don't want any significant attenuation of the radiation, but at the same time we want to have enough interaction so they can maintain charge particle equilibrium. So let's talk about the size. Okay, the size, your choice. So the detector of your choice has to be relevant for your application. Okay, so of course, the smaller the detector, you will get less of signal, right? Less of ionization. The larger detector, you will have more signal. Okay, but what I'm saying here is, if the detector is too large, right, you will have poor spatial resolution. So say in this red dot, it is actually profiled, your beam is coming down, and then we're trying to measure the profile across, and you picked somewhat large detector, and then you're moving this across. Okay, what's going to happen is it's like this. So you measure across, and then you end up having this soft shoulder. Okay, so why this is happening? Because if you have the detector is too big for this steep dose gradient. Okay, so you end up you're underestimating the dose here, and you're overestimating those here because of this partial volume effect, you can call it. Okay, so physicist has to be very careful when you measure a profile or to characterize the shoulder, or if you want to measure the output for small field, you have to have a significantly smaller detector. So you may argue that air-filled ionization chamber is not very good solution for those type of situation. But typical water like electron beam, photon beam profile, you can use very, very small air ion chamber for the application, and I have some examples. What are the examples of this cavity ionization ion chamber? So here you see that we call it thimble chamber. That looks like a thimble. You know what thimble is, right? So when you do the sewing, you put a thimble on your finger, so it looks like a thimble chamber, or parallel plate chamber, or we call this well ionization chamber, or well type ionization chamber. So you can categorize this into three. So clinically, physicists in our department, we use all three different kinds depending on our application. Okay, so let's talk about thimble chambers first. So collecting volume, so the active volume of thimble chamber can vary from as small as like zero point 0.1 cc to 1 cc for our radiation therapy application, but it can be as big as like this for like health physics, radiation survey type of application. Okay, so let's look at this cartoon here. So you have air cavity inside, and you have a central central electrode, and then you have this inner wall, that is also electrode itself, the surface electrode. So you have a central electrode, and then wall electrode. The bias will be applied. When I say bias, like a voltage will be applied, either positive, negative, or negative, positive. And then whenever the radiation is coming through this, and what is happening is it ionizes the gas inside, air inside, and then because there is a voltage applied, the charge will be collected. So typically it is actually coupled with insulator to avoid any electric shock, or to avoid leakage of any signal going losing. We want to avoid any signal escaping. So we have a very, very small chamber, and as large as this environmental type of radiation measurement. Okay, so but you have to know this Farmer chamber. Okay, so this is our physics go-to chamber. So it is most commonly used for electron beam calibration. So most of you guys actually already learned the lecture about TG51, photon electron linear accelerator calibration. So that's our go-to chamber. Okay, so what is unique about this chamber? This chamber is the active volume is less than 1 cc, very, very small, and the wall is graphite. Okay, so there are different variations of this Farmer chamber. So we call it Farmer type chamber. So graphite is somewhat, you have to be careful not to break it. So there's a plastic version of this Farmer chamber that has a similar characteristics. So active volume of 0.6 cc is the same. And then again, so internal is very similar, right? So you have a central electrode, and then you have a graphite, and then the charge will be collected based on the bias it is applied, and then it is like serving as insulator. So I have a picture of Farmer chamber in next slide. So it looks something like this. So it has cover, because again, this graphite, if you're uncareful, you can actually break it. So we have a plastic cover. So we call this as a reference chamber, because when we say calibrate, that means we want to measure what is our machine output, right? When I deliver 100 mu, it has to deliver a certain amount of those at certain depth and certain field size. So we characterize that using this Farmer chamber. However, okay, we cannot accurately use this Farmer type chamber for beam profile measurement, because it is too big. Okay, so it is good for point dose measurement at a standard setup at depth, but it is never designed for profile measurement or depth dose, even depth dose measurement. Okay, so big no. Farmer chamber is not good for PDD measurement because it's too big. All right, so then what are the smaller thimble chamber examples? So this is beam profile measurement. This example, we call it CC13. The active volume is 0.13 cc. So I believe, let me see, do I have a pen? Okay, I have a pen. So again, Farmer chamber, 0.6 cc. This guy right here, 0.13 cc. Physically, it is smaller. And so this chamber, it is actually a submersible, so you can actually put this in under the water, and it is actually ideal for water phantom measurement. Okay, so it's not calibrated, but it is good for relative output measurement. So think about it, like PDD and profile, those are all relative measurement, right? So it's okay that you just need some relative number, and then that's perfectly fine. So just remember Farmer chamber, TG51, 10 cm depth, but not for profile measurement. And the small chamber, CC13 chamber, is perfect for constancy check or profile measurement, depth dose measurement type of things. Okay. So I just said that Farmer chamber is not good for shallow depth measurement, right? So shallow depths. So why? Because the presence of the chamber itself, it'll disturb the low energy electron beam near the surface. So then what do we do? What is the better? So I already mentioned the CC13 is a good example. You can use this. But if you really want to measure really, really accurate surface dose, CC13 might be not even actually a good example. So especially for electron where you have a very, very high gradient at the surface, and even photon, we have a special chamber for that purpose. Okay, so it's a plane parallel chamber, also parallel plane chamber. You can also say that. So what is special about this chamber? It is very, very thin. Okay, so when I say thin, it is active volume is very thin. So this thickness is very, very thin, this thickness. Okay, so it's as thin as 0.01 to like sub-millimeter. No, I'll take that back. It is rather like 2 millimeter, couple millimeter. And this window material, okay, is that thin. So again, we have to be very careful not to break this. Okay, so what do? We have this electric field. Okay, is there positively charged or negatively charged? Okay, so this shaded area is active volume, and where the electric field is rather straight. Okay, and that tiny volume, extremely small volume, is very, very ideal for surface dose measurement. So again, let's think about this. So this is actually cut out of parallel plane chamber. I have a picture actually next slide, but it's very, very small. And what is guard ring? Guard ring is there to, so without guard ring, electric field can actually bow out. Electric field, if I actually draw electric field, right? Something like this. So you can accidentally measure that is the volume outside of actual volume. But by introducing this guard ring, you can actually maintain the electric field, at least within this shaded area, straight. So you just measure what the event that is happening within that physical volume. Okay. So here's an example of parallel plate chamber. So the name for this chamber is Marcus chamber. It's active volume, that shaded volume that we saw earlier, is 0.02 cc, extremely small volume. Okay, so I really have to talk about this special kind of parallel plate chamber. So this thing called extrapolation chamber. So I personally don't have experience actually use this, but conceptually you can easily understand. So that active volume, this is special parallel plane chamber, that active volume, okay, that thin volume, in this special detector, you can adjust, okay, the separation of that volume. Okay, those two electrodes can be adjusted in very fine resolution. So your idea is, I'll just start with say 5 millimeter separation, and then you move, and then you extrapolate to 0, right? So physically, we cannot measure 0 thickness volume, but by having this adjustable, meter, you can sort of extrapolate your data so that you can get the surface dose. Right? Does that make sense? Okay. All right. And lastly, the Weyl-ion chamber. So Weyl-ion chamber is ideally suited for brachytherapy seed, such as iodine-125 seed that we use for the eye plaque, and also like iridium-192 seed that we use for HDR. It's not seed, but HDR source. the source output can be measured using this well ion chamber. Okay, so you see the cross section of well ion chamber here. The wall itself is often filled with pressurized gas to increase signal to noise ratio. So you drop a seed or the radiation source, the HDR source that is connected to the cable, and then folds into here. Then the radiation will obviously come out every angle, right? Every direction, and then you measure the ionization within this wall. Okay, so if it is pressurized, sealed, then you don't have to correct for the temperature pressure correction. Yeah, so this picture here is actually the ion chamber that we use for the iodine 125 seed assay for IPLEX, and we connect this to the electrometer, and then you measure either charge or ampere. Okay, all right, so every ion chamber needs to be connected to this electrometer. So what is electrometer? Electrometer is well, it serves two purposes. I mean, so it applies a voltage, right? Bias. Typical range is not range. Typical actually we use negative 300 or positive 300. I'm sure some of you guys already learned that why we have these two different voltage setup, because we want to eliminate any additional bias, right? The uncertainty because of this bias voltage itself. But anyway, that's another story. But anyway, typically we apply either positive 300 or negative 300, and then also it collects. Okay, so it applies voltage, but also it collects the charges. Okay, so it is a very high precision machine, so it can measure like a nanocoulomb range. Okay, so what do we do with this device? So we connect this, this to the thimble chamber or well ion chamber, and this device itself needs to be recalibrated every 2 years. So along with those ion chambers that I mentioned earlier. So especially farmer type chamber or well ion chamber that we use, we send this with the electrometer to this accredited calibration lab, national lab at Wisconsin. It's not national, but it's a accredited lab in Wisconsin every 2 years. So these air-filled, gas-filled ion chambers, unless it is pressurized and sealed, you always have to talk about this pressure and temperature correction. Okay, so it is only valid for the vented ionization chamber, so vented chamber that I mentioned earlier. So it is like, the temperature and pressure inside that active volume changes, as your environmental pressure and volume changes. So the standard reference is 22 centigrade and 760 milligram mercury. So temperature goes up. What happened? Temperature goes up, then the molecules bounce around, and then the active absolute number of air molecule within the active volume will go down. Yes, it will go down, and then you will have less of ionization as compared to the lower temperature. So you have to correct for that by increasing. This number will go higher than 1. Okay, what happened to the when pressure goes up, that number of molecule will go up, and then you have to compensate that. Okay, vice versa. All right, so that's it. So rather short lecture today, but next week we'll review some other type of detector, which is actually very, very important for our department or in our field. GM counter, proportional detectors. It's just conceptually we have to learn, and then solid state detectors such as TLD, OSLD, films, diodes, MOSFETs, and gel, and then some calorimeters and chemical dosimeter. which is not clinical, but they love to ask about this. So, all right. So sorry again. I have to record this because I have a clinical obligation at the same time. But hopefully this format still serves you, well. So if you have any question, feel free to reach out to me, or you can stop by my office or send me an email. Okay. All right. I'll also give you guys the RayFX questions from past several years. All right, guys. Thank you so much. See you next week.